Parents how things. This is the undamped model. So I suppose we were given our initial displacement and our initial velocity. We were given them in the properties of the question. We were given our mass as 3,000 kgs and our stiffness as 600,000 Newton per meter. So what we done first was we calculated our natural frequency. This was got by the square root of k over m. I suppose this formula is just shown here. We then use this equation. We use this to actually calculate our initial conditions, which are A and B. A is known as U naught, which is the initial displacement, and B is V naught over W, which is the initial velocity over the natural frequency. By subbing these values into this formula, I plug them in here into this cell and I pull them down. I use the time step as 0.01 to try and give a smooth curve, and just gives a more accurate result. I think I took this to go down as far as about 5.1 seconds there, be seen in the graph, or 1.5 seconds even. I suppose that's just the damp system. I suppose if we added a velocity here, it would change the amplitude. The initial displacement wouldn't be the maximum amplitude. It would actually change. In this case, also, if we change the initial velocity, which we can do there now, let's see the way it changes the graph. The initial displacement the initial amplitude goes up further, but at the same time, the max amplitude is the same top and bottom. Just change that back to 0. In our undamped system then, so we had a few initial conditions again. It was the same properties: the initial displacement, initial velocity, the mass, stiffness. I suppose we got our natural frequency again. This time we had this dampening coefficient. This dampening coefficient for one part of the question was 2% and the other part was 5%. The greater the dampening coefficient, the faster the system will come into equilibrium. This here again I used a 0.1 time step just to give a smooth curve. I suppose we had two equations here which I would like to satisfy for the underdamped model. These were the equation U here equals E, the exponential of zeta, omega nt, etc. And I also used the equation, this one here, sorry, U equals the amplitude of the exponential minus zeta omega nt cos omega t minus the phase angle. So I just like to satisfy that the two of them were the same. So what I did for the first one was I used this formula here, but to do this I had to get my dampening frequency, which was got using the formula the natural frequency square root 1 minus the dampening coefficient. So that formula there can be seen there, which gives us our value. Once we had that got in, we had our time. We had to get our A and B values. Our A and B values differed from the two A and B values in the previous example, the undamped. Here A is the same as U naught, but B differs. It's the initial velocity plus the initial displacement times zeta times the natural frequency all over the damped frequency. So once we got these velocities, or got these initial conditions, we plugged them into the equation for the underdamped model. And what we done was we put them into here, and the equation there, we put them down for however long the time it done for. For my own sake, I done it for this equation here as well, just to satisfy that they were true. So I suppose U here is the amplitude, and E is the exponential. We have zeta, which if I didn't mention previously, zeta is the dampening coefficient there, 2%. And we have our natural frequency times the time. We just call it the dampening coefficient, which we got minus the phase angle. The phase angle was something which which we had to calculate. So what we done was there was a formula there. It was 10 times the phase angle is equal to V naught plus the initial velocity plus the initial displacement times zeta. But what we had to do was we had to rearrange this just to get us the phase angle. So when we calculated out this, which I have done up here, phase angle here. So I put it in there. That, so that gave us our phase angle. Or u, I'm actually incorrect. Or u wasn't the initial velocity. Or u was our u naught squared plus our u naught squared, which there must have been a formula for that too, which I have in here. It's don't see that formula anywhere there, but if I must have seen it in the notes. Basically we just put that in, we sub them values in for u, we get out our value of u there to be 0.05. I suppose what we done then was we got the exponential equation to get the amplitude decaying line. This was given by the first half of this equation here. But in this equation there was also an a term, but sometimes this isn't put in as it is a redundant number. So we use this function to get the rate of decay with time, to get u of t, the amplitude at different time t as it is decaying. So what I done was I put in our values back into this, and I also put in the a value at the start, which in this case was our u naught, our initial displacement. Just this is the minus exponential then, just to get it coming up from the bottom. See the bottom phase angle, which is over. So this is the first equation, and this is the second equation which we done out. As they can see, they're the exact same, and I just overlapped them there on one another just to prove that they are the same. Next part was pretty much the same, only the next section which we did have to do here was we had to get the number of cycles to reach the limit displacement and get the time taken. So basically for the graphical method, what we done was we put in an amplitude limit. So for the 20% u max, which was 20% of 50, so which is 10 millimeters, I put in not 10 millimeters. This gave us our lines going straight across the graph. This was where the amplitude limit line crosses our amplitude decaying line. What we done was that was the number of cycles which it took. That's the number of cycles it took to reach the limit displacement. So what we done was we could read off the graph. So for this one, it was approximately 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12.7, I'd imagine there, somewhere around that. And we could read off the time as being 5.7 roughly. And when we actually come up here to do the formula numerically, which is this formula here, what we do is we rearrange it to get j. So as you can see here, I have my 2 pi epsilon. There's an epsilon there, which I put in this minute. 2 pi epsilon there, which gives us 1.6, and then I also got ln of, in this case it is a 20% reduction, so I have ln of 0.2 in here. Yeah, so once we got in that formula in, we just banged it in to get j, which was just the ln divided by 2 pi zeta I mean. So I must put in zeta there. So then to get our time we actually had to get the natural period of the system. The natural period of the system was got from the natural frequency. So it's just 2 pi all over the natural frequency. So to get the time taken, what we done was we multiplied the number of cycles by the natural period of the system. So that is there. That gives us that value. I suppose what else have I to do? Just go through. I suppose it was just the same for the next part there. only we changed our dampening coefficient value to 5%. By changing this value, obviously it changed our damping ratio, damping frequency, and we can see as what we can see is that it reduces the time taken for it to increase the damping coefficient. Reduces the time for the system to come into equilibrium. So you can just see there, it reduces that. The natural period stays the same. All other values stay the same. Obviously, if we put in a VO value, it'll increase our phase angle. Obviously, in this case, our phase angle also changes because we have a new dampening coefficient in. But if we were to put in a value here, it would actually increase our phase angle again, which would reduce the one period for one oscillation to occur. I suppose what else have I to say? Just this is the dampening period, and that was calculated by 2 pi over omega n 1 minus the zeta. I think that's pretty much everything there now. Hopefully that was okay for you, Terence, and thanks.